Okay, thank you so much for the invitation. So, I would like to talk about some uh, series of work of about Ricci Flow and about their application. So, um, let me s- let me start with some motivation of the object that I want to study and why I want to study it. So a very rough motivation is I want to study this kind of object which is non-negative and positive AVR manifolds and then just beyond just before we talk about Ricci flow, just let's see what else we know in general first. So we know because of Ricci curvature and because of the EVR is positive, then we can always consider the blow down manifold because we want to study the infinity of a manifold. So we blow it down by just some subsequence and randomly, and then we know there's some metric space is whether which blow down is convergence. So this is just by straightforward application of Gromov in the context Gromov-Hausdorff topology. And then one of the very important point is that because it's brought down of a original of a fixed manifold, so this metric space obtained in this way must be isometric to a metric cone. So that means it's not general metric space, it's some very special metric space because the metric cone is self-similar. And then the very generic question is under what condition we can say something about this metric space, this metric cone, C sigma, and I'm particularly interested in the case when the metric space is actually regular. So I mean, by regular I mean so metrically it can be singular, but maybe topologically it's fine. It's not that bad. And if this is the case, then I want to say whether we can recover the original manifold structure. Like if we know something about the metric cone, then can we say something about the original manifolds, etc. So what I care most is about the original manifold, but we just want to say something from the metric cone infinity. Okay, so this is the very general motivation, and of course, this too general, like the Ricci law negative API response is extremely weak. So the that's why I want to impose something, but the something is the question. Okay, so this this very general question I want to study some from the Ricci flow point of view because Ricci flow is trying to smooth out the manifold. I mean, if you define it appropriately, so let's say for now, let's say we can find the Ricci flow. So what I mean is I can let's say I have another smooth manifold such that I can talk about the Ricci flow on that smooth manifold. But at the same time, when t goes to zero, I don't require the smooth initial data. I only require the initial data as a Gromov-Hausdorff metric space. So in this way, this you can see in this way, this is essentially a smoothing process, just a approximation in the Gromov-Hausdorff topology, but at the same time, the Ricci flow is a smooth candidate. Okay, so it's smoothing out the metric space. Okay, so then okay, so because I want to ask whether I want to understand this guy, so of course I can want to smooth it out, but Ricci flow is I one of the okay, depends on who you ask, but it's it's likely the most canonical way to smooth out something. So that's why I want to study this guy. And then if this is the case, if I have such flow or such equation solution, then what is the expected behavior of this guy? Okay, because it's not arbitrary initial data. The initial data is a metric cone. And then you can also ask what kind of estimate do we expect on this Ricci flow if sigma is not so singular. Is for example, if sigma is just something like a sphere but not standard metric, then then what else you can expect on this guy? Okay, things like this. Okay, all right. So this is the one of the motivation behind and let's take a look on some also special case, but general enough. Because the metric cone is a self-similar, right? So you can rescale the metric so such that it just radially we scale radially, so the radial scaling is also uh, compensating the scaling of metric. So this basically Moore is saying this is true, right? Because we can if you pretend the initial data as something smooth, let's just pretend it's smooth, then self-similar basically says that the rescale of this guy is an isometry. Okay. So if okay, also pretending we have this as good properties as the smooth case and compact case, then because of this, then the rescaling is unique. So I mean the solution is unique. So therefore you have such a conclusion. Okay, because the scaling is the same. So you by uniqueness you get uh, the self-similar structure of the Ricci flow. Okay, so this completely self-similar. So you can just pretend R is T with T. So basically, it says that this is a self-similar solution of a solution Ricci flow. In this case, you're actually moving forward in time, in all positive time. So in this case, usually people study the Ricci flow by imposing the self-similar structure, and in particular, the more interesting case is if the self-similar structure is in form of some gradient flow, then this is called then the corresponding equation is called the expanding Ricci sort, gradient expanding Ricci sort, which is captured by this equation. Okay, so this is the self-similar solution modeling the cone. Okay, modeling the cone. And then in the case the sigma, if we okay, because we want to ask whether it's movable, so therefore if you impose the smooth estimate on this guy, on this guy, then automatically you can see that because this is a scaling of the original data. So if you impose smoothness on G1, then you automatically have this estimate. So yeah, so also automatically has this estimate. So this is a scaling invariant curvature decay when t go from 0 to positive time. So you suddenly have bounded curvature. You can put it this way. Okay. So this is the object that we want to study. Okay. So you can see this is a Ricci flow modeling the metric cone. Okay. Modeling the smoothing out of a metric cone. Okay. So that is why you can now turn it into a concrete problem. Now, so the concrete problem is to ask okay, given a complete manifold just like what we started or something similar, under what additional assumption you can solve this guy. Okay, you can solve this guy quantitatively. By quantitatively, I mean you can solve it with estimate. Okay, so without estimate, it's too general. But let's say I want to ask something with estimate with okay. So because this is Ricci flow modeling the cone. Okay, so modeling the cone. So if you draw a graph, so if you sorry. If you draw a graph, so if you draw a graph, this is a cone, then the Ricci flow coming out of it is like this. So we're moving outward, moving outward. Okay, so this is the Ricci flow dynamic coming out of the cone. Okay. Okay. All right. So this is the model that I want to study. Okay. So the reason why, because okay, if this is if you can find some conditions so that I can solve this quantitatively, then I can replace the initial data by the rescale object so that I can flowing this guy, I can flowing any with flow down of the initial data. And when you keep doing this as as the speed goes to infinity, then you basically are finding the Ricci flow coming out of the metric cone because this is supposed to be close to be the metric cone. Okay. Okay, if you can have a answer to this question, then you basically can find the condition you can flow the cone, flow those cone which is movable. Okay, so this is the motivation. Okay. Um, Okay, so you can also ask from the PD point of view. This is geometry viewpoint. Before we talk about the exact application, this is some smoothability of metric cone problem. You can also ask similar question like can we have uniqueness, can we have stability, etc. So under this condition, any case is interesting. In my opinion, for example, if so as I've said, the most interesting object that we care is the metric cone itself. But if you think about the metric cone as a limit of the blowdown, then each blowdown is also an interesting object that we should consider first, maybe. So which is the smooth initial data case. Okay, yeah, before we pass it to the metric cone, this is the smooth case, and or if we are more aggressive or more ambitious, and we should, and then we should talk about the uniqueness and stability in the singular case when the initial data is metric cone. Okay, so this is a PD question. For this at this stage, this is a PD question. Okay, okay. And one of the difficult point why this is interesting, but at the same time not straightforward from the PDE is because the Ricci Flow equation is diffeomorphic invariant. So if you forget about the initial data for a moment, just focusing on the equation itself as diffeomorphic invariant. So that means if you want to appeal to PDE method, then you don't have a suitable gauge to fix it. So finding a good gauge for you to apply Ricci Flow is actually non-trivial because you need whether you can fix the gauge is already a problem in Ricci Flow. Okay, in MCF it's always doable because you can do it by graph. I mean, sorry, in codimension one mean curvature flow case is trivial because locally you can do it by graph, but in Ricci Flow there's no such thing. So fixing a gauge is always a big problem here. Okay, so this PD aspect, this is an interesting question. But okay, I will talk about the application later, but let me uh, gi- just give you a quick overview of what we know first. Okay, so let me focus on the existence. So I think quite interestingly, usually existence is a harder in general, but in this question, the existence I think is easier in some sense. Um, but still, it's not as easy as you thought. The general question is just even if have a smooth metric initial data, okay, under what condition can we find the Ricci flows coming out of it? So as I have said, this is nonlinear, and diffeomorphic invariant it's actually weakly parabolic because of this. So it's in general unclear whether you can always solve the equation or not, unless you are in compact case. But okay, as I have said in the motivation, so I'm always interested in the long compact case. So the first result is by Shi, where he proved the short time existence under bounded curvature. So its bounded curvature is not modeled in the cone. If in the cone category, the bounded curvature basically means flat. So because just always keep in mind we are more interested in cone today. Okay. And but anyway, he built the first fundamental result in Ricci flow theory, and given the topping, they've developed the whole complete theory for surface for two-dimensional Riemann manifold. So in a sense, if you only focus on smooth initial data, I think they pretty much developed the complete theory. So nothing can be said more. And okay, to my expertise, I think Esther and Berger is the first one constructing short time existence under very unbounded curvature. So they consider the so-called non-negative complex sectional curvature, or to the expert in retrieval and minimal surface, they consider the pick two case, weakly pick two case. So they in that case they can always find short time existence. So no matter how crazy the infinity, no matter what, because this is a very strong convex condition, is always can be evolved for short time. But unfortunately, they don't have good estimate because this is the only assumption they have. They didn't put into account the initial data is a cone, so it's very general. It can be collapsing. That's the beauty of the work. But nonetheless, they can prove short time existence no matter what extra assumption on the so regardless of any assumption on the infinity. Okay. So this is uh the result. And then in the last, I think in the last 7 years or 8 years, there's many development in the field about existence theory in Ricci Flow. So those all of them are independent of boundary curvature. That's let me just I think I list all except for Hotcher. So basically in the cone case, so all of them can be localized in a greater extent, but let me just focusing on the cone case. So all of them in 3 dimension, they are if you have Ricci curvature, so which is exactly the scenario that I start with, or the Kähler case, if you assume the initial data is Kähler, but with so-called orthogonal bisectional curvature, or if you're more familiar with the classical one, then you just pretend this is bisectional curvature, something really strong enough to do classification. Just if you have no idea what they are, just think of Kähler geometry with curvature, which is strong enough to classify. Okay, to classify the compact case. Okay, and also there's a generalization of Ricci curvature in high dimension about which is called pick one, weakly pick one. So it's a generalization of Ricci curvature in the sense of Lie algebra. Okay, and so in all these cases, if you have complete manifold with positive AVR and either one of them is true, then you can always find the Ricci flow for a long time, actually for a long time. And the curvature is decayed in a scaling way. So it's exactly the one I described at the very beginning. So in particular, in this case, the manifold must be diffeomorphic to Euclidean space. Okay, must be diffeomorphic to Euclidean space. So this is what I want to. That's just one part of the motivation I said. So in this case, you can always smooth out the metric cone at infinity. Okay, because you can smooth it out, then the manifold must be topological Euclidean. Okay, it must be diffeomorphic to Euclidean space. Okay, so this is a very important progress in retrieval existence theory, and so I put a remark here to illustrate the strength of the curvature in Riemannian case. So the very strong curvature condition is called non-negative curvature operator, which is the strongest possible cone, so which is the smallest one, and a subset of the so-called the pick two cone, which is the condition studied by Esther and Burkhardt in the previous slides. And the pick one is the weaker one. In 3D, they are the same. With this one, they are the same. In 3 dimension, the Ricci curvature cone is the same as the pick one cone, but in high dimension, they are different. And also in 3D case, the pick two cone is the sectional curvature cone. Okay, but in high dimension, it's also stronger. Okay, so these are the some result in Ricci flow theory. Okay, and then all right, so that's why I want to study the Ricci flow from cone This is okay. Any questions so far? Okay, and okay, then so so it basically says that if you have strong enough curvature, then the cone at infinity can be smooth. You can just put it this way. So there's a question by Felix. I think he put it in a very rough term, but roughly speaking, he want to ask, okay, so in the case previously discussed, you can throw it. Okay, fine, happy. Okay, let's put it in a more general framework. So let's say if you have Ricci flow coming out of the cone in pointer Gromov-Hausdorff sense, and the Ricci flow has good estimates as curvature law negative and scaling invariant. So which is the case stronger than some of the case in the last slide. So this all these are weaker. Okay, all these are weaker. So this is a weaker than curvature. This is weaker than curvature. This is weaker than curvature. Okay, just forget about this first. Just pretend this is the stronger possible long, curvature. Then he want to ask whether this Ricci flow is uniquely determined by the cone itself. He want to ask things like this. Okay. So the reason why is because there's some motivation from what he did with Miles and Alex, so which I'm going to talk about. So he's not just studying the cone. I mean, for fun. He want to study because we are all interested in the following problem around the same time from different perspectives. So this is a motivation behind the question he raised. So at least I think it's a motivation. Actually, I don't know when he make the conjecture, but I think he make it around the same time all of us are solving this problem. So this is a problem I think attribute to Hamilton, but anyway, so this is called people refer it as a Hamilton pinching conjecture. He basically asks if in a three-dimensional manifold complete, then if the Ricci curvature is stronger than non-negative, is pinched by the scalar curvature. So you can see in this way, everything is scaling invariant. So if you scale this, then this will be scaled at the same time. So this inequality is scaling invariant. Then the manifold itself either is compact. In the compact case, we know from Hamilton it's a sphere. Sorry, I mean it's a sphere space form, or it's flat. Okay. So in the non-compact case, it's actually saying that you can't have too much positive. You can't have any positive curvature if you have pinching in this way. Okay. So this is a first study by Chen and Zhu long time ago, I think 25 years ago. And then in the last few years, we consider this problem and eventually solve it by John. He is the first one we studying it, and then Alex, Felix, and Miles. Also myself with Peter are trying to contribute. I contribute each part of it and completely answer this question. Okay, so this is based on the Ricci flow. Okay. All right, so let me try to explain why this is okay. At this stage, apparently this has nothing to do with what I said. It's just a Riemannian problem, right? So the one of the very interesting observation by John is the following. So he basically he didn't put it in this way, but this is essentially what he proved. He discovered that okay, in a three-dimensional, we can classify the smooth structure very easily, right? Because of Sun and Yao, we know if the curvature is positive, then it must be diffeomorphic to Euclidean space. And he observed that okay, if you can find a Ricci flow coming out of it in a scaling invariant way like this, so basically saying that if you have okay, I don't have a metric cone right now because there's no positive AVR. But let's say if I do it in the opposite way, I already have a smoother with all the matching estimate. Then in this case, the AVR must be positive. There's no collapsing happening. Okay, he has such very interesting observation. Actually, very important theorem to us. Okay, so in fact, in the Kata cases also observed by Chow and Tam, but in using a completely different method. So yeah, and then okay, so once you so he basically build up a connection from the long collapsing and the Ricci flow existence. So the smoothing is equivalent to long collapsing. non-collapsing is equivalent smoothing. So they are one correspondent basically in three-dimensional case at least. So using this, myself and Peter uh, is able to uh, justify what he need here. So we can say that okay, even without long collapsing, as long as we have Ricci pinching in three dimension, we can always find the metric cone. We can always find the Ricci flow. In particular, from John, we know that then it implies the AVI is positive, and because of this, then we can run the game of metric cone. So yeah, that's our contribution is saying that okay, retrieval existence is true regardless of the metric cone picture is in the pinching case. So okay, so then then the question is asking okay, now you have smoothing and now you have a cone picture now in mind. So how rigid is the Ricci flow? So then because I want to study this guy. I mean you just turn the problem into a Ricci flow is not necessarily helpful, right? And the very nice, very interesting observation is by Alex, Felix, and Miles is saying that okay, let's pretending we have a self-similar structure. So like I said, so just let's pretend the self-similar structure. Then you have expanding which is Solton. Okay, let's pretend this is true. And if it is expanding which is Solton, it's more and more rigid because at first you have no equation. It's an open condition. It's an inequality condition. Now you have an equality condition. So things becomes more and more rigid, right? It's an elliptic problem now. So on top of the elliptic problem, we have a pinching. Okay, we have pinching. Then it's just a very simple ODE. You can prove that the curvature will decay very fast at infinity. Because of self-similar Solton structure, you can prove this by ODE. You can prove this one by some very simple ODE. And because the curvature decays so fast, so there's a bunch of classical theorem in classical gap theorem in Riemann geometry, particularly by Green and Wu. They basically say that the curvature cannot be too small at infinity unless it's flat, because we are in the non-negative curvature case, pretty much non-negative rigid curvature. And then so this is the baby model they have in mind. Actually, this is actually this is the argument originally by Chen and Drew. Okay, once you have this, you just want to show that you have self-similar structure as we predict. Okay, and Alexa and Felix and Miles, they are not exactly proving the equality. They're not able to prove the Solton structure in the full generality, but it's not far from it. The point is they can prove that the equation is not far from being self-similar, and it's exactly good enough to run the above argument. So in particular, they know the Ricci flow coming out of a cone is actually a flat one. So you can use it to prove the rigidity. Okay, so that's why that is how they they prove this one. Okay, this is how they prove the rigidity. So okay, this is how they prove the rigidity. Okay, all right. So this is uh the progress. I mean the full solution that we all have. Um, and then now so of course is from the from the viewpoint of the problem is basically solved, so there's nothing else you can say, but it raises a natural question. So of course they can prove that the Ricci flow construct in this way is not far from being expanding Solton. Then you can ask generally speaking, under what condition you can resolve a cone by expander? So just a very general question. So just given you a metric cone, I mean, because from the motivation question, we know it should be resolved by an expander. So let's then now we take it seriously. When is it really the case? Okay. I'm just try collect all the main theorem that I know related to this question. So in the smoothable case, a long time ago is by Charlton and Brendel, and also Felix and Miles. They consider the case when the cone is smoothable. So smoothable by strong enough curvature. So this is by Hana, by so-called by the Hana inequality, and this is a dynamic. What they prove is the dynamic rigidity, and and as an elliptic problem, you can also ask the same questions. Just give you a metric cone. When can you resolve this by expander, right? So this is I think the first one considering this is by uh, uh, Brian. So I think he considered he considered the case when the sigma is actually sphere. So it's a sphere with all the invariant. Sorry, it's a standard sphere basically. Uh, and then but not the standard sphere, just a shrinking sphere. And it is later considered by Durrell. He considered the case when the sphere is just some metric with sufficiently positive curvature. And then so this is a good case. And then there are some progress by Ricci and Eric Chan. They consider the case when the curvature is only in terms of scalar curvature, but in 3 dimension, I think. And there's a very interesting problem work by Ackerman and Danoff. They construct some very strange expanding soliton coming out of cone, which is not unique. So they are able to find more than one way to resolve metric cone by expander. Okay, in high dimension. Okay, so in a so but for us, we are more interested in the first one because this is the one which appear naturally in Chiga coding theory. All the rest are smooth. So this smooth K, this smooth K, this smooth K, this smooth K. So we are more interested in the first case where the sigma is obtained from Chiga coding theory. But uh, yeah. So but the problem is that if you focusing on this case, then the sigma has no regularity, right? Because it's just abstract compactness from Gromov. Okay, so this is the case I'm interested in. Actually, we are interested. Okay, it looks very complicated. Let me just go through it slowly. So, like I said, so pretending this is 3 dimensions, so therefore this is just a Ricci curvature. So just pretend this is Ricci curvature in 3 dimension. Uh, the higher that just pretending this is a Ricci non-negative cone in 3D. So we with Chen and Pichi, we are able to improve the result by by Alex, Felix, and Mao. So we basically say that what they can prove has imposed some condition, and we are able to remove all of them. So all the metric cone in this way must be resolved by expanding soliton. So let me just go through this. So if it's a Ricci non-negative curvature in 3D, positive AVR, then I can always find a smooth Ricci flow such that this Ricci flow is actually regularizing the metric cone. So it's smoothing out the metric cone. And more importantly, this Ricci flow is automatically expanding soliton. It's automatically a gradient expanding soliton. Okay. And it's more importantly, the gradient vector field is in terms of function, which is converging back to the distance square. So it's a conical metric. It's converging to the conical metric. So in some topology, in some appropriate topology. Okay. Okay. So in other words, that means as long as the initial data is a metric cone and the Ricci flow has strong curvature, then it's automatically expanding solve. So this is some rigidity I prove with Patya and Luke. Okay. and improving their result. And in Kayla case, there's some interesting analog. I don't want to go through it. Just keep in mind there are some parallel case in Kayla. But I just want to mention the Kayla case is very different from Riemannian case. It's only solid in some particular directions, but not solid in all directions. I mean, using the same method. It's very interesting that in the Riemannian, I mean, usually Kayla is more rigid. I mean, usually Kayla is uh, I won't say easier, but usually there's if you find the correct assumption, then Riemannian case should have Kayla case and Riemann case should almost the same if you find the correct uh, condition to work with. But in this method, it's not. At least I can't achieve the same things. I can only do some I mean half of the result that I'm looking for. Okay, but anyway, so okay. So going back to the expanding soliton, one of the most interesting application again is the with pinching problem in high dimension. So we in fact this is the motivation why we study the stability. Uh, in fact they study the stability in their paper. So and and they study how close it can be from an experience or along. It's a stability types argument in their paper. Okay. Okay, so as an application of everything I said, so I mean by combining the two group, we now know that if it's complete non-compact and it's the pinch in the cone of a pick one. Okay, so in 3D it just reduce back to the Hamilton pinching conjecture. I mean pinching theorem now. In high dimension, this is not the same, but if you are willing to strengthen the curvature from Ricci to pick one, then you still have flatness. Either you assume the AVR is positive, so this is the missing pieces, or if you are willing to impose pick two, then you don't have to impose the positive AVR, then the manifold is automatically flat. So it's yes, okay. So in particular, so let me put it this way. So in particular, pick two, it is so maybe if you're not familiar with the Ricci flow, then it doesn't look very I mean not natural. No, I don't I maybe you even no idea what they are. So the pick two is implied by the quarter pinch condition in the differentiable sphere realm. So just put it this way. So the pick two is the natural condition which is implied by the differentiable sphere realm. And the pick one is actually weaker. Okay, so it's a weaker, even weaker condition, which is implied by the quarter pinch condition in the differentiable sphere. So, okay, and then the overall idea is uh, still we are able to construct a Ricci flow with estimate without volume growth condition, and then it will particularly imply AVR is positive if you assume the pick two. If you assume pick two, or if you assume, then of course, if you assume it's open up a cone, then we know this is the you can find a smoothing of the cone at infinity by expander. If you have no idea, but if you are willing to assume something stronger, then you still can the curvature will still allow you to open up the manifolds and put it this, open up the manifold. We use some again. We use some important observation by Esther and Burkhardt in their paper. But anyway, okay. So this is rigid. Okay. So that's why this is one of the main motivation forcing me to study the uniqueness and existence. Okay, but this is a very special case of uniqueness. It's not the full uniqueness. It's just a partial uniqueness because I'm not proving the Ricci flow is unique. I'm just proving that as the Ricci flow is self-similar, not relying on the uniqueness. Okay, so supposedly it's a self-cinema because of uniqueness, but we are not able to prove it by this method. We are able to prove it directly. We are not proving the expansion order by uniqueness. We're just finding the gradient vector field actually. Okay, then because of this, so then you naturally ask, okay, seems very evidence that the Ricci flow is unique in this class, but uh, in more appropriate term, I mean more concrete term, then that means that if we have two Ricci flows on a fixed manifolds, which is not defined at zero, okay, it's only defined as zero in a weak sense here. So they both define on the same manifold, but distantly converge to the same metric space. Then you ask whether they are the same, right? Okay, just I'm yeah, there's a precise way to express the problem. Okay, and uh okay, you can see I make this in part of the proposal. Um, it's not consistent with the soliton, and you also at the same time you can also forget about this, right? I mean, you can ask the same question if you impose no condition on the curvature lower bound. However, as I have said, even if you assume they are expanding soliton, uh, they are not necessarily unique because of example by Ackermann and Deng. So in some sense, I mean, let me put it this way. So they actually they prove they construct a non-unique example without the middle condition. They are able to prove a non-unique example without the middle condition. Okay, without the middle condition. So therefore, the main interesting question now is what if you have some curvature condition on the lower bar, So it's very strong in I mean, that's not extremely strong, but it's imposing some analytic condition on the PD itself. And this question is actually considered by Alex, Felix, and Miles again. But they consider the case when the initial data is Weissenberg. So they are not considering this in the full generality. They just consider the special case where the initial data is Euclidean space. They can even localize it. So the more interesting case they can localize it is they can localize and prove that it's not far from Euclidean. And if it's global, then it's actually Euclidean. Okay. Okay. Then yeah. Uh, okay. So this is yep. Okay. So all right. So this is the uniqueness in general, which is not known yet. So that the general case is still fully unclear to us, to all of us, and so that's why I consider. I mean, I think the same problem has been considered in the past by many people. Uh, so so let me step back a little bit and consider the smooth case. So I'm considering the smooth case, but complete non-compact. So you can think of this case as a singularity at infinity. So there's no singularity on any compact region, but the singularity is always at infinity. Okay, which is uh kind of I mean, we basically consider blow down, but not taking limit. We just consider each candidate in the blow down, but not taking the limit. Okay. So this is actually this is a classical problem in Ricci flow. First studied by Chen and Zhu. When they studied also 20 years ago, 23 years ago, yeah. They studied the Ricci flow uniqueness. And later, more recently, I think 10 years, around 10 years ago, Kosha, we considered this problem. So this is the statement I known from Kosha. So it can stay as follows. So if the uniqueness is true if you assume the curvature is bounded from above by something like this. But this is scaling invariant. Sorry, this is not scaling invariant. Not scaling invariant. So this is saying that if the curvature is bound, even if it's unbounded, it's not so unbounded. It's just some uh, small than critical one. Then the Ricci Flow is unique. Okay, so if we think about the regularity, so this is of course, this is not consistent with the cone because the cone is the case when gamma is 1. So, but this is not consistent with the cone. But he basically says that on the asymptotic level, if it's not far from being a Weissenberg, then we are fine. Then we are fine. If we are not far from being Weissenberg, then we're fine. Actually, Cosworth has it's not even necessarily assuming the curvature. I think you only need some Ricci curvature condition is sufficient. I mean, it's not necessarily assuming this full condition. I just put it in this way so that it's easier to understand. Okay, so he proved this. And as a downside of Cosworth's result, he's using energy method. So this importance of this band basically saying that the gauge is automatically fixed. Okay, the gauge is always fixed because because it's integrable, so you can always fix the gauge easily. You don't have to pick the gauge. You can always fix a natural gauge by initial data, for example, by the initial G0 as a gauge. So, again, as I have said, this the more interesting case is gamma is 1, which is a cone. The cone is when gamma is okay. So this is the model case. So, but as you can see in this way that the uniqueness is still a difficult problem. And then because of the motivation because I mean thanks to the development in the recent year, I reconsider this question, and I can prove the case when gamma is 1. Okay, in a smooth case, So I assume the initial data is smoothly attained at 0. Right? So this is very important, smoothly attained at 0. So I can prove the Ricci Flow is unique in this case. And as I've said, so Ackerman and North, they build up the counterexample to this related problem when the initial data is not attained in C infinity topology. They if you assume the initial data are just Gromov-Hausdorff very rough initial attainment, then the corresponding result is not true. Okay, they have counterexample. So this is only true when you have an attainment here smoothly. Okay, this is smoothly, or I think at least a C4 or C3. I forgot how. I haven't traced it, but at least some regularity is important. Some not quantitatively, but some regularity of the attainment is important here. Okay, in general, and then we are in fact built on optimal version of the Chenzhou method. So I think it's an interesting method that I want to say something about it, and yeah. So the method here is built on so-called the harmonic map, built on the classical one. Sorry, I should say. Oh, sorry, I should mention Hamilton is the first one considered the compact case. I forgot to put this. So, and Chenzhou is essentially making use of Hamilton's method, but because it's non-compact, so they need more effort to justify everything involved in Hamilton's original method. And now the point is we can localize. Okay, we can localize the Hamilton method, or you can localize the method by Chenzhou. So the interesting part is if you have two Ricci flow defined for simplicity, just pretend they are defined on complete region, defined on a complete whole manifold, but it's only necessary everything is on a compact region. So if the statement saying that if you have a Ricci flow and the control is scaling invariant, so that means locally you just pretend this is a Ricci Flow defined nearby the tips of the cone. Okay, but however, they define it in a tensorial way so that they equal, okay, equals to the initial data. The initial data equal as a tensor smoothly. Then I can always find a solution to the harmonic map heat flow, coupled between these two guys. So we are not taking a random reference. We are taking the reference from G to G tilde. We are to fix a reference G and G tilde. So in this way, I can always solve it. I can always solve it in a way that it starts from initial data to be identity. Okay, initial gauge is the constant gauge, and modulus this harmonic map, the Ricci flow will be comparable locally. It's just locally we can always compare locally, and it's compared in asymptotically in any order here. Asymptotically is in any order. So it basically says that if you have a local region where there's a two geometric flow starting from there, and the control is not crazy, just some scaling invariant. It's not crazy unbounded. It's unbounded, but in the correct scale. Then after you run the flow, so of course the Ricci flow is a semi-local, so it can go to it can drift to infinity very fast. However, in this C over T condition, you can always compare two guy along the flow in a way that their difference is always up to T to power something. So they can always be comparable. So that means they can't go crazily falling apart to each other. They always compare in a comparable way. Okay, along the evolution. So in particular, they are smoothly comparable. In particular, smoothly comparable. Okay, so after you do scaling, you can use it to prove uniqueness. So the point is the quantitative here is everything is quantitative here. It just depends on the C. Okay, depends on the constant here. Okay, so in a way, in short term, that means that means we fix the gauge by harmonic map locally. Locally. Okay. It has some application in some metric geometry, but yeah, I don't want to spend too much time there because I'm not an expert. Yeah, people told me there's an application from this. Yeah, so yeah, let me not spend too much time here. So this is uniqueness, but however, it's important to emphasize that the initial data must be in tensorial sense because I'm relying on so-called the Ricci flow or the harmonic map heat flow. So we need something like a equal. I need something on the tensorial level that are equal. I need something like this. So this is one of the key points that involved in the analysis. And yeah, so in general, Ricci flow uniqueness I believe must be interpreted in this way because Ricci flow is diffeomorphic invariant, so you have to find a way to gauge it. Okay, so for MCF it's different because you can always gauge it naturally by graph, so there's no such things by so-called gauge in some sense. But for Ricci flow, the gauge will also be changing along the time. So therefore, the Ricci flow uniqueness and existence must be sorry. The Ricci flow uniqueness and stability has to be, I believe, has to be phrased in this way. Okay. So okay, so this is a uniqueness, and then very recently we pick up the stability problem for some other reason, and and we can prove the stability in some sense, also in some sense. Yes, yeah. We still want to consider the stability of Ricci flow coming out of cone. Okay, but like I said, the initial data is always a headache. For our purpose or our application in our mind, we are not studying the PD problem only. We want to use it to study some sort of problem. So it's fine to assume that initial time is smooth in that application. So we consider the quantitative case first, and with Chen and Lai, we consider the case when it's actually the Ricci Flow model in the cone here. So as you can see, the curvature is bound from below. If you do scaling, is you can pretend this is just a zero, and you can pretend this guy is zero, and pretend this t is infinite. And then along such Ricci flow, we are able to put some the weak stability of the Ricci flow. So which basically says that if you have an initial data sufficiently close to it, then it always admit a, or I should mention this is unique. So admit a unique Ricci data flow starting from this guy, such that it stay close to each other along the flow, stay close to each other. It's not falling apart instantaneously. So it's different from the previous one. The previous one I need equal, but now I'm saying that if they're not far from each other, then it's stay not far from each other along the flow. So as you can see, this is modeled in the cone. So it's essentially say that the cone, you perturb a cone a little bit, you can always flow it and stay close to the original expanding cone nearby the central expander. And yeah, so there's some application to soliton. I'm not sure if I think it's interesting, but I think that yeah. So as an application of this stability, we have some steady soliton existent film, which says that we can construct more soliton, steady soliton, steady. Sorry. It's a steady soliton here. So we can use it to construct more steady soliton with non-negative curvature with more prescribed symmetry group. Okay, as an application of the stability film. I think I should stop here. Okay, thank you so much.